Today we're going to finish our discussion of geometric transformations and hopefully move into one more piece that we're going to talk about this semester for a different type of geometry. So last time we were looking at, we're just going to see where we left off. Did I talk about parallel displacement?
That was the last thing we talked about.
That's the last one we talked about? This one. Fantastic. That's where I thought it was. Good. All right, so we're going to actually talk about a little bit more about parallel displacement today. And one more transformation, actually, called a glide. So to start with, the parallel displacement, just to remind you where we were last time in hyperbolic geometry, L and M can be parallel without having a common perpendicular. That's called asymptotically parallel. And in this case, that transformation would be a composition of reflections called a parallel displacement. And I think, yeah, we'll do this particular picture with the Klein model. Okay, so the Klein model can display this idea. So we're going to draw ourselves a circle. And remember, in a Klein model, the lines are chords of the circle. So if we had a chord here, oh, that's dotted from before. If we have a chord here and a chord here that meet on the edge of the circle, those would actually still be parallel because they don't meet in the circle. So this would be L and M. And we could create the pole. Not that it's going to be created perfectly because certainly I'm doing it on the iPad, but pretend for a moment. Oops. Approximately like this. And we have our pole on the other side, and it's actually going to be, hang on, I know that's not right, but I'm moving it, so fear not. And here's our pole on our other side. So this one right here would be the pole of M. We'll call it P of M. There's a pole up on the top that's P of L. And this is the sigma. And so we have the parallel displacement of these lines of reflection. So if I had, let's see, I think the point P is showing up right here. This point would actually reflect onto the other side of this. And then we would end up getting it reflected up to here, and this would be P prime. So that's parallel displacement. It doesn't actually look quite the same as it did in Euclidean geometry. In Euclidean geometry, it just looked like it sort of shifted along the side of the page, right? But in the Klein model, it almost looks like it rotated because parallel lines don't have this equidistant sort of a feature to them. So some facts about parallel displacements. Let me pause long enough to make sure you guys have the picture. I'm sorry. Before I flip my page.
Why was it necessary to find the poles?
My picture has the poles from what I was looking at. I think it has to do with how the reflections are happening to show it on there. I'm not remembering the details of why they're drawn in, to be honest with you right now, Sheena.
Okay.
Yeah. But the reflection does not end up looking like a slide, like it's just slid over in that particular model, which is what I wanted to show. So, yeah. All right.
Wait, is this the parallel displacement thing?
Yeah.
Okay, so you just like take the inverses and then
Mm-hmm.
like. Okay.
Yeah. All right, so some facts about parallel displacement. There's a lot of facts we could talk about. We're just going to mention, I think I've got about 4 of them to talk about. So we're going to let T be a transformation translation, excuse me, but it is transformation too. And a translation is the composition of two reflections, which we've talked about before. And this is going to be a parallel displacement. Where specifically L and M are asymptotically parallel. In the direction of the ideal point sigma. And where ideal points are the ones that are along the edge of the circle. So our first fact is that this translation has no ordinary fixed points. Nothing will be fixed by the double reflection. The second one is that this transformation, this translation, has no invariant lines. We've talked about invariant before. Remember, it means that the lines are unchanged even if the points switch locations on them, the lines are in the same location. We don't have those here. The third one is that the only ideal fixed point of T is sigma, because sigma lies on both of those lines that we're reflecting over, of course. And the last point that we're going to mention is that a motion with exactly one ideal fixed point is a parallel displacement. Okay, so having just that one fixed point is both necessary and sufficient for it to be parallel displacement. I mentioned we had one more transformation we were going to talk about, and it is called a glide. So the definition is that a glide, sometimes called a glide reflection, just so you know, but a glide along T is a motion of the form T prime, which is a reflection over the line T after the translation T, where T is the non-identity, or is a non-identity, not the. Translation along T. Thus, this glide is actually 3 reflections. Okay.
Is lowercase t and capital T two different things?
They are. The capital T is our transformation. It's a translation that we've been talking about. The lowercase t is a line itself. So lowercase t is just a line that we're using to translate along. One more detail here. This is where T is perpendicular to L and T is perpendicular to M. I'll draw you a picture as we write down a few of our facts in our next slide. So we've got 2 parallel lines, L and M, and T is perpendicular to both of them, okay? That's what we have. We're translating, which we've talked about shifting, along the line. In this case, it's T, but we're translating across these 2 reflections, and then we're going to reflect it over the perpendicular line afterwards. One of the pictures that you can kind of have in mind is footprints along the sand, right? So the footprints are a reflection across the line of symmetry that would be between them, correct? So you have these idea of these footprints going, the footprints go across, the footprint on the left continues, that would be a translation, and then the reflection to the other side of where the footprint would be a reflection. So that's actually called a glide or a glide reflection. So your image looks something like this. Has to have a common perpendicular, okay? So common perpendiculars don't necessarily have to exist, but for us to talk about a glide, they do. That's what they are. So here is L, and here is M, and this is the lowercase t that we're talking about, Shayna. So when we're working with this translation, if we start, say, over here, and then we translate, of course, what we know that means is that this gets shifted this way. Okay, we're going to translate that direction because we're translating across M first because it's the inner transformation. Remember, compositions work from the inside out, so we start here. So we first reflect over line M, and then we're going to reflect over line L, and then reflect over line T. So we're working from the inside out. So this transformation right here will end up shifting this and moving it over okay, this isn't working well. There we go. Here. So we've done a reflection twice. It ends up being a translation over to here if we've done it correctly. All right, and then it reflects again over line T. So we end up getting the image to be down here, something like that. Okay, so it's glided and it's reflected. It's a slide transformation. Okay, a few facts about glides. All right, fact number 1 is that this glide is a composition of reflections, and it's actually able to be done in this order as well. So if you imagine coming up to my picture at the top, what I could have done is if I'd reflected it over line T first and then translated it, I would have gotten the same image when I was done. Right? So it isn't all of it commutative. Sorry, that's definitely a picture I wrote down wrong. I got carried away. I was talking while I was writing. That's RL and this is RM. I'm so sorry. It's not all commutative. We aren't moving everything around, but the final reflection over line T can happen first or it can happen last, like commutativity, okay? That part of it is. So let's let B be the point where M intersects T. So that would be here. Then hang on, I don't know what I wrote down here, just a moment. Okay. Our transformation, which we had said was our composition of these reflections. So if we were to reflect like this, whoops, it would actually be the same as taking a half turn around point B and then reflecting it over line L. And I'll show you an image in that in a minute. What that means is that thus a glide is uniquely determined by a line L and a point B not on L. So if I were to make a half turn around point B to start with, remember the order is from the inside out, so we do our half turn first. Sorry, these are compositions. Even in my notes, I'm getting a little bit too relaxed about that. Our half turn, if I'm drawing it right, I think ends up being like this, roughly speaking. Does that sound right to you guys? Look right? If I rotate it around halfway, around point B, it's going to be approximately here. And then I get a reflection over line L to put me here. My spacing's a little bit off, but can you imagine if I'd done it with my spacing right? I think I can move this over a little bit. That would probably help. How's that? That's a little bit more believable. So we've got our half turn followed by a reflection. One more fact for this. Glides have no fixed points. And leave invariant only line T. Okay, we have one, maybe two more slides here about transformational geometry, and then we're going to change directions. So a definition and a theorem. Definition: a motion is called direct. Or orientation preserving. If it is the product of two reflections. It is called opposite or orientation reversing. If it is a reflection, so just a simple reflection, not two reflections, or a glide. And a glide is actually what we just learned. How many reflections? 3. It was 3 reflections. So an even number of reflections ends up being orientation preserving or direct, and an odd number of reflections, 1 or 3. And we only have those options, by the way, right? We have the identity, we have 1 reflection, 2 reflections, or 3 reflections. All of our transformations can be done with one of those options. We talked about that a couple of days ago. So they're all going to either fall into that 2 reflection category or an odd number of reflection category, in which case they are orientation reversing. So I'll draw a picture of this idea, and then I'm going to have one theorem for you. Whoops. That's what I thought I had. Okay, so if we have our line L here, and I'm going to draw a triangle over here like this. Whoops. There we go. Then the orientation, if we do 1 reflection over this line, it's not perfect. It's not even close. That's not too bad. It's smaller, but pretend for a moment that I just reflected it and it's actually the right size, okay? So I can copy paste, but I can't copy paste and reflect. That doesn't work like that. So the idea is that if we had this sort of a clockwise movement going, we talked about the object going in this orientation. When it gets reflected, all of the orientation gets reflected as well. So we end up having our orientation looking like this as a part of the reflection process, and it goes like that. So if you reflect twice, of course, it would flip it back to where it was before, so we would preserve our orientation. So theorem 9.1, every motion this is what I was just saying, every motion is either direct or opposite, and clearly not both. Furthermore, the set of direct motions is a group. And the product or composition of 2 opposite motions like 2 reflections is direct. Whereas the product of a direct motion and an opposite motion is opposite. Proving this is pretty direct. It's pretty straightforward. It goes back to the fact that we can translate all of this language back into reflections, okay? So our definition actually said that we've either got a direct or an opposite. Those are the 2 options here. And we know that when we have a reflection or a glide, we have an odd number of reflections. And when we have what did I have? 2 reflections, which is the other fact in our definition, that it's a direct relationship. So each of these options, so if I have a direct motion combined with an opposite motion, direct meant that there were 2 reflections, opposite meant there's either 1 or 3, right? And when we combine these together, we get an odd number. So you have an odd number of reflections, so it's opposite. When we take an even number, or we take an opposite motion with another opposite motion, those were both odd reflection numbers to begin with. And when we take something that's odd and we add them together, we get an even number of reflections. Hence, it would become a direct motion. So that's what's going on there in terms of the proof.